Hello and welcome to this vSuite version 0.6 video tutorial, and in this video tutorial I'm going to cover some of the basics of doing an OpenFOAM CFD simulation with the FloVi component of the vSuite. So it should just say right now, as of vSuite version 0.6, FloVi and OpenFOAM is only really supported on Linux. Hopefully version 0.6.1 will have the ability to do it on OS X and Windows as well, if I'm lucky. But at the moment this is a Linux only workflow. And I work on Arch Linux, so it's only really known to work on Arch Linux. I don't run any other Linux distributions. But with any luck it will work on different Linux distributions as well. So one of the first things you have to do if you're going to do a FloVi analysis is that we're going to need an OpenFOAM installation on your Linux computer, and I'm using OpenFOAM 8 from the sort of open freely available community edition of OpenFOAM, and we need to tell the vSuite where that installation is. So if I just come into my preferences and I come down to the vSuite, I can open up the options here, and it's this OpenFOAM binary directory that we will need to set. So if I open that up, we will see that my OpenFOAM installation is in opt OpenFOAM, and the directory we require here is, for me, OpenFOAM-8 bin directory, and it is this foam exec file. That's the file that should be in the directory that we select here. So accept that, and then once you've set that, you may need to restart Blender to make sure it's registered in, but that now should see my OpenFOAM installation. So the next thing we have to do is we have to create geometry. There are two types of FloVi geometry in the vSuite. There's CFD domain and there's CFD geometry. I might talk about geometry a little bit more in another video, but I'm just going to concentrate on the domain in this video. And the domain is the sort of overall domain for the simulation. So it's where all the fluid flow will be calculated. So I've got here, and this is analysis I did for work of Brighton seafront, and this geometry represents the complete domain that we're going to be doing our simulation within. Now there are some important things to remember when specifying CFD domains and CFD geometry. The most important thing is that the geometry must be manifold. It must form a complete shell, which in simple terms means that every edge has to be connected to two faces, and there are no gaps within the geometry. Now Blender does have quite a nice utility to allow us to check if a mesh has any non-manifold geometry. So if I click on this object and I go into edit mode and I deselect everything, then if I'm in edge select mode here, and I might just go to wireframe as well so that we can see what's going on. If I press, for me it's F3, depends on your Blender settings, but, and you can see I had it selected earlier. If I start tapping in non, I will have this select non-manifold option. If I click on that, we should see nothing get highlighted. This means that all the geometry here is manifold, all the edges linked to two faces, and it forms a consistent shell. If, for example, I was to do something like this, so now I've got a big hole here, and these edges, these four edges, are only connected to one face. If I was to now go back into edge select mode, select non-manifold, you would see that those edges are now selected because they are non-manifold. So make sure that your geometry for both a CFD domain and CFD geometry is completely manifold. So this object is manifold, so that's fine. Now the next thing I've done is that I've come into my object properties panel, and in my vSuite object definition I have selected CFD domain for this object. So that's now identified it as a domain geometry. Now I have to identify the boundary conditions of the faces, and this is done through the material system. So if I come down to the material properties tab, you'll see that I've got 4 materials associated with this geometry. So if I can now select, I'm in edit mode, and I can select geometry based on the material. So this is the geometry or the faces of my object which have this ground material associated with it. These are my 2 or 3, what I'm calling my sides boundary, and I've got an in boundary here. So my airflow is going to come this way, and I've got an out boundary here. So my air is going to leave through this face. So once you've set materials to the requisite faces, then we need to define what those materials are, or what they mean in terms of OpenFOAM and in terms of an OpenFOAM boundary condition. So let's take the ground first, and I've just coloured them so that you can see. It could be useful to colour when you create the materials. It can be useful to give them a colour so that you can see clearly where they've been associated in terms of your model. So the ground I've given a sort of reddish brown colour, and if I scroll down in my vSuite material section, I can see that instead of geometry or a light sensor, I've specified this as a flovy boundary. And there are some options here. One is to set, when we do the mesh, when we subdivide this boundary, when we subdivide this domain up for the simulation, this number here, net gen max cell size, will define how big the cells are on this ground boundary. We then have type. Now type is important because you need to set these first, ideally. Other options we can change later on quite quickly, but you need to set these types correctly before you proceed. So the ground is a wall, it's a physical obstruction, and it's got a pressure type of 0 gradient, a U type of no slip, and all these options, even I don't really know what they mean. They're sort of OpenFOAM boundary conditions. So you will need to know what the boundary conditions are, what they mean, so that you can pick the right one for your particular model. And the OpenFOAM distribution comes with lots of example files, which will give you examples of the boundary conditions that have been used for different kinds of simulation. The vSuite doesn't try and be clever for you in that respect. The vSuite just takes your input and tries to create valid OpenFOAM output based on that input. So if your simulations don't converge or they don't work, I can't help you with that, because for a start I'm not knowledgeable enough. But if you're inputting something into the vSuite interface and it's producing an OpenFOAM input files which are not in accordance with that, then that's a vSuite bug, and I can try and fix that. So yeah, you will need to get a handle on what these boundary condition options mean for yourself. It's the same with sides. Sides, these are symmetry boundaries, so I consider What's happening inside of this boundary is the same as what's happening on the outside, and it's the same for the top and the other side. So that's simple, just set that to symmetry. In is an inflow. Now for an in, we want patch. So if there's any airflow movement across the boundary, in or out, we would want the patch type. And then again, there are different options for the different boundary conditions that you can associate with the patch type. The important thing for me here is the velocity value, because this boundary represents an inflow, so we're going to have some flow coming in. So if this is my in boundary, sorry, that's not, this is my in boundary, so I want my flow to come in, which is in the opposite x direction in blender space. So x minus 5 meters per second, y0, z0. Out boundary, here we have total pressure. Again, it's a patch type because air is moving out of the domain at this point, so we choose patch. And again, options are to be understood in terms of OpenFOAM boundaries. So that's the geometry and the boundary material sort of specification. And now we can create some FloVi nodes to start the process of simulation. So I will just make a quick note about CFD geometry as well as CFD domain. We can also have some geometry. So I've got a little cube here that I just created, and I could put that cube in that space, and then in my object properties I would specify this as CFD geometry rather than CFD domain. And as long as that object geometry is manifold and the basic Blender cube is manifold, then that would be a perfectly valid thing to do. And I would give that a material, and I would specify wall probably as a boundary condition, and that will be part of the simulation. But if I was to do something like this, where this CFD geometry straddles the domain boundary, so some of it is inside and some of it is outside, that's not legal. I use NetGen as the mesher, and NetGen, at the time of making this video at least, doesn't allow overlapping geometry. So any CFD geometry has to sit completely within the domain, and then it should function properly. But I'm not going to use that here. I'm just going to do the flow through this ground terrain, which is the bottom of my overall CFD domain. So if I come to my vSuite Nodes tab, then I've got a FloVi case node. Now a FloVi case node is added through the process nodes FloVi case menu entry. And it will start off like this. So in this FloVi case node, there are a number of options, and they're detailed to some extent in the vSuite user manual. We have whether to do a steady state or transient analysis, but only steady state is working right now. We can pick our turbulence model, time steps within the simulation, overall end time for the simulation. If we had thermal effects here, we can turn on buoyancy. We can give residual values for convergence. We can give initial values to the domain. So these are speed, for example, would be the initial speed within the domain when we start the simulation. Again, check out the OpenFOAM documentation about what all these mean. But once I've got these set up the way I want, then if I press export, then I can now link this to a FloVi NetGen node. Now again, this is added through process nodes FloVi NetGen. Connect this in, and here I've got options for mesh generation. So this is the cell size within the domain in general, or kind of a maximum cell size. cells can be smaller depending on geometric features and any cell size you've set for your particular boundary conditions. Position core, embarrassingly, I can't remember what that's for. You'll have to check the vSuite user manual. Angular core, same again. If I say it now, I'll say it wrong. So again, I'll refer you to the user manual. Distinction angle, same again. Very embarrassing, I know. Inflation, I do remember what that's about. That's if you've got small cells, because you set a boundary which has got very small cells on it, and you've got larger cells within the domain, then this is how quickly the small cells become big cells. So the lower this number, the slower small cells will become big cells. And once you've done a few mesh visualizations, you'll see what the impact of that is. Optimization sets the number of optimizations. At the end of mesh generation, NetGen can go through a process of optimizing that mesh so that you get the best aspect ratio, you get the best formulation of the mesh within your domain. So, and I generally use 3. And then this final Boolean flag is to turn on polygonal mesh. NetGen will produce a tetrahedral mesh. I like polygonal meshes. I don't know why, I just really like them. So there is an option here to turn on converting the tetrahedral mesh generated by NetGen into a polygonal mesh with OpenFOAM. So if I don't have that on, then in a few seconds I will have generated a mesh, a tetrahedral mesh. Now currently that tetrahedral mesh doesn't get visualized in Blender. Again, that will probably be something I enable for version 0.6.1. There is a way to visualize it, which I'll show you in a moment. If we turn on polygonal, then if I generate that mesh, this will take a little bit longer now, because with polygonal turned on, we will get a visualization of the mesh within Blender. So there we go, there is our mesh within our domain. If I turn off the original object from visibility and I turn on wireframe, then we can see that polygonal mesh. If you want to look in the mesh, you can do that. I suppose there are a number of ways. You can change the clip on the 3D view, so that just sets the distant range that we can see within a 3D viewport. So as I turn up the clip, I'm clipping off anything closer to the camera so I can get a simple appreciation of the mesh in that very simple way. I can also go into edit mode, and because the boundary materials are associated with the faces of this mesh as they were with the original domain object, then if I come to my material tab, then what I can do is I can, for example, if I deselect everything, I've got a material associated with all the internal. Well, what I might do is I might pick sides first, select all the elements of that mesh with the sides material, and then I can press H to hide them. And then I can do the same with the volume, and I can press H to hide them. So we're just hiding it from the 3D viewport. The mesh is still there. But then you get to see the internal surface distribution of our polygonal mesh. If I come out of edit mode, and if I go back in, that stuff is still hidden. What you can do is press Alt H, and then everything will be visible again within the 3D viewport. So that is the mesh. Now that I've got a mesh, I can connect that mesh into a flovy boundary node. Now what a flovy boundary node does is this case node, if I come to the material tab, then this case node, what it would have done is it would have taken the geometry and the mesh specification in terms of what faces they're associated with, and it would have taken this type parameter, and this case node takes that data. But if we want to change something, so we've set the patch, so we know it's an inflow or an outflow, but we want to start changing velocities or the pressure boundaries, that data gets written out with the flovy boundary node. So I can generate a flovy boundary node now, and if I changed, I've just opened up ParaView, hold on a sec, I'll come to that in a moment, turn off that. If I change something here, so if I change the velocity of my inflow, I could change that here, and I could just press flovy boundary again. If I change it from a patch to a wall, however, if I change this type menu, I would have to come back and I would have to re-export my case as well. Now, if I just turn off polygonal, if I re-export that mesh, but it's going to be a tetrahedral mesh now, not a polygonal mesh, then I can't visualize that in Blender currently, but if I turn on this ParaView option within the flovy boundary node, if I now generate that, then hopefully I can now see. Now this is ParaView, and I'm not going to go into the details of how to use ParaView, but it's really good at visualizing CFD results, and currently there's no way within the V Suite to visualize CFD results. I just use ParaView. But there you can see the tetrahedral mesh. So this is the mesh produced by NetGen, and if polygonal is turned on, then we convert that into a polygonal mesh. So now that boundary has been calculated, or the boundary details have been written out for my model, then I can now come into my flovy simulation node. So I've got 8 logical processors on my laptop, so I'm going to turn this to 8. Again, I've got a ParaView flag here. If I turn this on, ParaView will automatically open up once I finish the simulation. If you don't have this turned on, then you have to open up the project.foam file in the project directory with OpenFOAM. And just while I think about that, this Blender file has been saved to blah 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 flovy.blend. So if I come into the directory where that blend file has been stored, so here's my flovy.blend file, within the same directory I will have a flovy directory. So this is the V Suite project directory, and this is where livy and envy all save data associated with a particular Blender file. And in that flovy folder, which is in the same directory as the flovy.blend, I've got this OpenFOAM folder, and here I've got all these different things, which some of these I specified before because I've run through this simulation before, and you'll have this project.foam file, and you can open that project.foam file with OpenFOAM. So if you don't specify ParaView here, you can still open that foam file with ParaView to visualize your results. But I will keep it on here. I click on that now, and we'll get a Kivy window pop up. So the Kivy window, like all the other Kivy windows, it gives you a indication of progress. But in this case, the progress isn't the amount of time to complete the simulation, because when we're doing a CFD simulation, we don't know how long it's going to take for us to reach a solution. So what the Kiwi window shows you instead is, for all the different parameters that we're solving, pressure, velocities, k and epsilon, it will show you the current residual within the simulation. So those residual values are set down here. So once the residual for each of our parameters has gone below a certain level, then the simulation will stop. So that was quite quick, and ParaView has opened up. Excuse me. And we can now see we've got our simulation loaded up with our simulation data. So yeah, like I say, I'm not going to do any particular instruction on ParaView here, but you can create slices, you can create glyphs, which always comes in too high by default. And we can see there's our velocity streamlines, for example. The plane is coloured with pressure. So yeah, ParaView gives you a lot of flexibility and options for simulating different types of or analysing different types of parameter. So for a very beginning of using OpenFOAM, I think that's more or less everything I want to cover right now. So, okay, thanks for watching. Oh, I should, there's always something. I should say, if you want to use multi-processes on your Linux machine, then you will also, not only will you need to install OpenFOAM, but you will also need to install OpenMPI. Otherwise you'll just have to put in one in here to do a simulation. And I think that then is everything. Okay, thanks then. Cheers then. Bye.